Scientists have developed a building material that lives and can reproduce. Researchers from the University of Colorado have developed a building material that lives. It is a mixture of sand and cyanobacteria and several other ingredients. The new material can grow and repair cracks on its own, and has a much smaller carbon footprint. What's more, it can reproduce. Scientists have shown that one parent brick can produce up to 8 bricks in 3 generations. Cement and concrete production has changed little over the last 100 years. The work of researchers from Colorado is something completely new in this field. The method they developed, presented in the magazine Matter, combines sand and bacteria, resulting in the creation of a living material with structural load-bearing capacity and biological function. We already use biological materials in our buildings, such as wood. But these materials are no longer living. But why can't we keep them alive and let biology do something useful too? Said Will Srubar, one of the authors of the publication and head of the Living Materials Laboratory at the University of Colorado, Boulder. The authors of the publication admitted that living buildings are not just a melody of the distant future. The technology they have developed, primarily for keeping bacteria alive, has several advantages that the technologies currently used in construction cannot provide. Structures created using living materials may one day seal their own cracks or suck in dangerous toxins from the air. The material developed by engineers has a scaffold of sand and hydrogel. The hydrogel retains moisture and nutrients so that bacteria can multiply and mineralize, a process similar to the formation of shells in the ocean. By combining cyanobacteria, hydrogel and sand, scientists have created a living material that has similar strength to cement mortar. The researchers experimented with cyanobacteria belonging to the genus Senecococcus. Under appropriate conditions, these microorganisms absorb carbon dioxide, which stimulates their growth. They produce calcium carbonate, which is one of the ingredients in the production of concrete and cement. We use photosynthetic cyanobacteria to biomineralize the scaffold. It's kind of like Frankenstein material. But that's what we're trying to create, something that stays alive, Srubar noted. The material developed by American scientists is not only a living building material, but can also regenerate. By splitting a brick of such material in half, adding hydrogel, sand, nutrients and water, the bacteria can grow into 2 complete bricks. Srubar and his team showed that one parent brick can reproduce up to 8 bricks in 3 generations. We are excited that this is challenging conventional ways of producing building materials. This really shows the possibilities of exponential material production, Srubar emphasized. Living brick must be completely dried to achieve maximum strength. However, drying impairs the viability of cyanobacteria. To maintain structural function and ensure microbial survival, the concept of optimal humidity and storage conditions is crucial. By using humidity and temperature, researchers can control when bacteria grow and when the material goes dormant to perform structural functions. It is a materials platform that sets the stage for exciting new materials that can be designed to work together and respond to their environment. We're just trying to revitalize building materials. We are laying the foundations of a new discipline, said Srubar. The next step for Srubar and his team is to explore the numerous applications that the materials platform he mentioned brings. Sruba envisions introducing bacteria with different functions to create new materials with biological functions, such as materials that detect and respond to toxins in the air. Other applications include building structures in places where resources are limited, such as a desert, or even another planet, Mars. In harsh environments, these materials would be particularly good because they use sunlight to grow and multiply with very little exogenous material needed to grow them. There will be no need to carry bags of cement all the way to Mars, Sruba explained. The solution created by Californian researchers is also ecological. Global production of cement and concrete for construction purposes generates almost 6% annual carbon dioxide emissions. As an added bonus, such bricks would actually remove carbon dioxide from the air, using it for growth. 100% melanoma vaccine. Effectiveness in tests on mice. An experimental vaccine against skin cancer, which increases the immune system's ability to fight the disease, has been 100% effective. Effectiveness in tests on mice. The new melanoma vaccine, developed by researchers from Scripps Research Institute in California in cooperation with colleagues from the University of Texas Southwestern Medical Center, contains an immunotherapy drug and a chemical that increases its effectiveness. The results of work on the vaccine were published in the Proceedings of the National Academy of Science. Scientists were able to demonstrate that their new therapy could fight cancer recurrence. The vaccine could also work with other therapies to fight extremely aggressive cancers. Our therapy produces a complete response in the treatment of melanoma, said Dale Boger of Scripps Research Institute in California, co-author of the paper. Just as any vaccine can train the body to fight external pathogens, ours will train the immune system to deal with cancer, he added. During the study, scientists analyzed over 100,000 compounds to find those that could help them increase the effectiveness of the cancer immunotherapy drug. Eventually, they found a chemical called diprovicin that binds to an immune receptor called toll-like receptor, TLR, in both humans and mice. The next step was to start testing on genetically modified mice with an aggressive form of melanoma. All mice received an anti-cancer drug called anti-PD-L1. The mice were divided into 3 groups. 8 received a cancer vaccine. Another 8 rodents received the same vaccine, anti-PD-L1 plus diprovicin. And the last 8 mice received the vaccine together with an alternative adjuvant, a compound intended to enhance the body's post-vaccination immune response, aluminum sulfate. The diprovicin molecule added to the vaccine triggers the body's immune response. It acts as an adjuvant. It is easy to synthesize in the laboratory and easy to modify, which makes it attractive for use in medicine. After 54 days of the experiment, scientists observed 100% survival rate in mice given the cancer vaccine and diprovicin. In the group of rodents that received only the anti-PD-L1 vaccine, no animals survived. Of the last group of mice given the vaccine plus an alternative adjuvant, 25% survived. Creatures. The rodents received 2 injections 1 week apart. The researchers did not inject directly into the tumor because they wanted to see if the immune system would make it easier for the compounds to reach the tumor directly. Further studies have shown that using diprovacim as an adjuvant increases the vaccine's potential in the fight against cancer by stimulating the immune system to produce a special type of leukocytes that can penetrate the tumor. Interestingly, attempts to re-induce melanoma in the mice that survived the study failed too. The animal is already vaccinated against it, Boger explained. This is a big step forward towards cancer immunotherapy. Although the research was conducted on rodents, the experimental results are extremely promising. Scientists now plan to conduct further preclinical studies with the developed vaccine and investigate how it works in combination with other cancer therapies.